Hi, this video covers applying the linear recursion pattern to singly linked lists. So we're going to look at doing operations on singly linked lists using recursion. First off, why? Why are we doing this? Well, the linear time list operations are a good fit for recursion. They fit that linear recursion pattern pretty clearly. There's a clear base case, which is like an empty list or nothing, and then a recursive case, which is when you have a node pointer and some stuff following it. So this is good practice in thinking about recursion and recursive thinking. Recursion is going to become essential when we get to trees. So these singly linked lists, you could code up a linear operation with a loop, or you could use recursion. It's kind of either or. But when we get to trees, there are some operations that are really a lot simpler and easier using recursion and very difficult with loops. So we need to kind of exercise this muscle. So list recursion, it's sort of half of tree recursion. Binary trees are kind of like linked lists, except they have 2 pointers instead of 1. So singly linked list recursion is kind of halfway there. So it's a good stepping stone to get up to recursive thinking on trees. And this exercise of doing list operations on linked lists will help you develop your recursive thinking and problem solving. This recursion is a major problem-solving approach in computer science, not just in data structures, but the whole field. And so it's something that computer scientists need to practice and get good at, and you do that by going through these kind of exercises. And these are used in practice in some programming languages. In functional languages like Lisp, Haskell, Scala, F#, and so forth, their main data structure is a singly linked list, and the standard way of repeating something is doing this kind of linear recursion. So if you're a programmer in those languages, you need to become pretty literate in this kind of recursive thinking. Here's the linear recursion pattern reviewing from the previous video. This is pseudocode, so I've got a recursive function. It takes an input of some kind. And if I'm in a base case, then I return a base case solution. So first we look at the input. If it's trivially small, then we just know what the answer is and we're done. Otherwise, we have a big piece of input. And so what we do is call a recursive function. So this function calls itself on a smaller input. So shave off a little bit of the input so it's a little smaller. We call ourselves on this smaller input. That gives us a sub-solution. That's the answer for everything else. And then we return a general solution that involves that sub-solution. So that's the general pattern. It's pretty abstract. Let's look at this in the concrete example of a singly linked list. So following this pattern, the recursive input is a node pointer. So we've got a pointer to a node. I would think to begin with, we point at the first element, the 7. That would be our first node. And then what is a node pointer really? Well, it contains either nothing. So if we start at the beginning and work our way to the right until we get to the end, a pointer to the dummy node has no elements in it. So a node pointer could have nothing in it at all. That would be the dummy pointer. Or a node pointer could have one element, like the 7, and another node pointer. And that other node pointer is kind of a recursive list. It's yet another list that's shorter. So the way that we apply this pattern, linear recursion in general, to a singly linked list pointer is that in the base case, if we're pointing at the dummy node, we've got no elements to deal with. That's the base case. If we're not pointing at the dummy node, we're pointing at a node that has an element. So let's call that the current node. And we deal with that. And then we call ourselves recursively on the rest of the list. That would be everything to the right of the current node. So that's the next pointer of the current node. Now, one detail here is the tail pointer or head pointer is a private data member. So that means that we can't make one of these recursive functions public because our caller would need to provide the argument of what node to start at, and they have no way of getting node pointers. So a workaround, it's a little clunky, but it works, is that we'll have to make our recursive function a private data member that takes a node pointer, and then there will have to be a public function that's not recursive. It just calls the recursive function to get it started using the tail pointer that points at a node. Okay, let's look at a concrete example to put this together. So let's say I just want to count the size of the linked list. It's a little bit redundant because our linked list does have a size data member. You might remember back when we were talking about alternatives that some singly linked lists don't actually keep track of their size. So let's say we want to count the size because we don't actually know what it is. So the base case would be the situation where we have nothing, which would be a pointer to the dummy node. How many elements are in a list if it only has a dummy node? 0. If there's no elements left, there are 0 elements by definition. Okay, the general case would be where I have a pointer to a node that has an element and it has the rest of the list. So what I need to do is recursively call myself on the rest of the list. That means count all of the elements after this current one, and then incorporate the current node, which accounts for a size of 1. If I have one node, that is one element that needs to be counted. So the general case solution is that the size of the list is 1 plus whatever the size of the remaining elements are. So let's look at this count size recursive function to begin with. This is the one that does most of the work. So it's given a pointer to a node, and to begin with, that is the first node that has an element in it. So if we were to run this code on this example, the first pointer is a pointer to the 7 node. Here's what it does. It says, if we're in the base case, return 0. So if the pointer points to the dummy node, there are no elements remaining, so return 0. That's the size of the list. And remember that the dummy node is tails next. So if pointer is equal to tail next, we're at the dummy node, return 0. Otherwise, what I do is call count size recursive on pointer next. So what that will do is count all of the nodes after this one. And we'll either get a positive number if there are nodes to the right, or we'll get 0 if this is the last node. So we get the size of everything after this node. I return 1 plus size of rest, because size of rest counts all of the elements after this one. The entire list has everything after this one plus this one, so there's one more than everything to the right. Finally, this has to be a private data member because this pointer cannot be obtained by the caller calling into the public part of the class. So we have a public function called count size. So note, the public function is called count size. It takes no arguments. The private function is called count size rec for recursive. It takes a pointer. And we call count size rec on the first element with a node, which in our circular dummy singly linked list is a little convoluted. It's tails next next. Why is it tail next next? Because that's the first element that has a element. Remember, tail is the last node. Next is the dummy node. Next again is the first element. So tail next next is a pointer to the first element containing node, which is the 7. So this works. This calculates the size. Let's kind of visualize how this works. So let's say I've got this same list. I've got 7, then 1, then 4, then the dummy node. So to begin with, I count size on the first node, which is the 7. So I'm counting the size of the 7, 1, 4 list. Our code will say, am I at the dummy node? If I'm at the dummy node, the answer is 0. Otherwise, the answer is 1 more than whatever the count of everything to the right is. So to begin with, am I at the dummy node? No. So the answer is 1 plus count size of the 1, 4 list, meaning everything to the right. So this function is paused while we call count size recursively on the second node. So what does that do? Okay, it's given a pointer pointing at the node containing 1, the second node in. We're counting the size of the part of the linked list starting at the 1 node. Is that the dummy node? No. So it's the general case. It's 1 plus whatever everything to the right is. So then we do a count size on the 4 node. Same logic. Is this the dummy node? No. So the answer is 1 plus whatever the size of everything to the right is. So we recursively call on the next pointer. That one is the dummy node. So what is the count size of the dummy node? That's the base case, which is 0. So count size of an empty list returns 0. And then that 0 is returned back to the count size starting at 4. Count size starting at 4 wants to return 1 plus the count size of everything to the right. So that's 1 plus the 0 that we got, which makes a total of 1. And then count size of 4 is finished. It returns back to this expression, count size of 1 and 4. It's trying to return the length of everything from 1 onwards, and it said that's 1 plus everything to the right. Everything to the right has 1 element, so that's 1 plus 1 makes 2. And then finally, we go back to the original count size, which was trying to calculate the list of everything, and it said that's 1 for the node that has the 7 plus everything to the right. Everything to the right is count size of 1 and 4, which has a size of 2. And so 1 plus 2 makes 3, and it returns 3, and that's actually the right answer. Let's look at another example. Let's say I want to return the ith element. So I want to implement the get I operation using recursion instead of a loop. We had an earlier video that did this with a loop. It worked with a skip function, but just as a thought exercise to practice recursive thinking, let's do this with recursion. So what I'm going to do is pass in the index I'm looking for. So the base case would be if I'm looking for index 0, then whatever node I'm at right now, that's the one. Index 0 is the beginning, the first node. But if I'm in the general case and I have an index I greater than 0, that means I need to skip over something. So if I've got a pointer to the beginning of the list and I want index 3 is the fourth element in, so I need to skip over some elements. So in the general case, I don't want the first element, I want a later one. I've got a node and I've got the rest of the list. So what I'm going to do is kind of peel off one node, just kind of cut off the first node and keep looking on everything that remains. So I'll return the I minus 1th element of the rest. Okay, here's how this could work. I've got my public function that works as usual for get. It's given an index I and it returns t. And I'm going to handle the case of a index that's bad in this function here. So if I is too big, throw an out of range exception. If we get past that, we know that I is a legal index, and I don't have to worry about that inside the recursion. Then I call my getRec function. So remember, get is the public function that the end user calls. It doesn't have a node pointer argument. GetRec is the actual recursive function that does the work, and it needs a pointer to a node. So again, I want to give it the first node that has an element, that's tail next next, as usual, and I'm looking for index I starting from this node. Now let's look at getRec that actually accomplishes this computation. It's given a pointer to a node, ptr, and a size ti, that's the index I'm looking for. The base case is if I want index number 0, the first element there is in the part of the list starting at this pointer, I return pointer element and I'm done. Otherwise, I need to skip past at least one node, and so I'll return get recursive of pointer next, so that moves to the right once. And now I want I minus 1th index, so I subtract 1 from I because I don't want the index to count from the original list. I'm continuing my search in a smaller part of the list off to the right, and so that index has to get subtracted by 1 to account for the fact that we shaved off one node right there.